Good morning, everybody. So I'm going to go first. My name is Mark Dredze. I'm a professor here in computer science, affiliated with the CLSP, and a research scientist at the Human Language Technology Center of Excellence. If you don't know what that is, you'll find out sometime this summer because it's just down the road, and you will no doubt be over there. What I'd like to talk about today is machine learning. So that was me, now you. So who here is an undergrad? Raise your hand. OK, great. Who here is a graduate student? Who here has their PhD already? Demianos didn't raise his hand. It's a little bit worrisome, if you ask me. But OK, great. I'm sorry, I didn't raise my hand either. OK, fair is fair. OK, great. So we're going to be talking about machine learning. So for those of you who have only been here for one day, which I assume is all of you, the way these tutorials tend to go is the first one tends to be kind of general introductory, and the second one tends to be a little more research focused. So I'm going first. I'm going to talk about machine learning in general. So what I want to do is give you kind of a large survey about different techniques and methods of machine learning. And then Gideon Mann is going to speak after me. He's not here yet, but hopefully he'll get here before I'm done. Otherwise, I'm just going to keep talking. And he's going to talk a little bit about some specific methods that he's working on and some really cool applications that they're doing at Google with these methods. So I saw some heads go up when I said Google, so maybe I'll just keep saying that to keep you awake. All right, so the first question is, does anyone want to tell me what machine learning is? Adventurous graduates, adventurous undergrads or graduates who already know the answer? I'll give you a hint. You can recompose words on the second line to come up with a definition. Someone. I'm not going on to the next slide until someone talks. No one wants?
Statistical patterns in data.
Finding statistical patterns in data. OK, good. That's good. It's not fair. I know Emily, so you can't keep doing this. So here's my definition. Teaching a computer about the world. But that sounds much better than mine, actually. So what does it mean to teach a computer about the world, right? I tell people all the time, like, I do machine learning, and they ask what it is. And I tell people, well, we're trying to teach computers about the world. And they think, like, I sit down with a computer and read a textbook or something. It's not really clear to me what they think I do. A lot of people also think I build killer robots, which is not really the focus of this summer school, but we could do that another time. But what I want to answer today, in trying to answer what does it mean to teach a computer about the world, is kind of introduce you to this way of thinking. What we do is we first make observations about the world. So sometimes that means walking around looking at things. Other times it means sitting in front of a computer looking at data. We try and develop models that match our observations. You saw a little bit of that in Jason's tutorial yesterday. You want to tag a sentence with something, and you tried to say, well, how are these tags likely to be generated? And then you want to teach a computer to learn these models, right? So you show the computer lots of data, and the computer figures out parameters of the model. And then now, once the computer knows that, it can apply to the world and do something interesting. So here are a bunch of pictures. If you search animal, I guess, on Google, you'll get pictures that look something like this. And there are a lot of different patterns that we can see in these pictures, we being humans. So I assume most people in this world can see patterns in these pictures. So what kind of patterns do you see here? What are ways to divide up these images into groups, for example?
Full length.
Full length versus not full length. OK. So this is a whole dog here. This is just the head of a bird. OK, that's good. What else? Yeah? Real versus stuffed animals. Yeah. So I'm not going to point which ones are real and stuffed. But if you have big questions, I'll answer it. Anyone else? Yeah?
Green background and white background.
Green background, white background. Good. What else? We'll go with one more. Yeah, I know. Everyone who got to go first took the easy ones. How about like mammals versus non-mammals, right? Everyone take biology. Remember what mammals are? OK, this is the non-mammal, by the way. I'm pretty sure that's a bird. Everything else I think is a mammal, but I'm not sure. So that's great. So basically, if I gave you these on index cards and asked you find patterns, you could all come up with different patterns. So when we give these to a computer, we want to ask the computer question. We want to ask certain questions about what that means, right? So it's pretty obvious to all of you what you do when you try and learn something about these pictures, right? There's a lot of things you can pick up on, a lot of patterns you can pick up on. Computers, we have to answer these questions. Well, what does it mean for a computer to learn something? How do we know computers learn something? What can the computer say, right? So you guys can give me, obviously, a huge range of answers. What kind of answers can a computer give me if I asked it the same question about these pictures? How do we represent these pictures or the world in general for computers, right? So you guys can just look at images, but what is an image to a computer? How does a computer understand that? From that, we'll talk a little bit about different motivations for what does it mean to learn and resulting learning algorithms that fall out of that. And then I want to touch on at the end of how do we guide machine learning, right? Now that we have these ideas, how do we tell a computer what we want to learn and guide its learning process? After that, Gideon's going to talk a little bit more detail about a specific machine learning framework of probabilistic models and methods, and he's going to talk about some real-world applications that he's been working with. So the first question is, what does it mean to learn, right? And I'm going to give this very generic answer: to learn patterns in data, right? So here's another way of classifying things. A system can learn when it takes pictures as input, like all you guys just did, and it outputs some information. In this case, I came up with the problem is this belongs in a house or this doesn't belong in a house. Right? So some of those pictures were things you'd see in someone's house. Some of those pictures were things you wouldn't see in someone's house. Let's assume a normal person's house, okay? But there was this guy on the Upper West Side a couple years ago who had like an alligator in his apartment. I don't know, does anyone remember this? He had like an alligator tiger. They found it because he was sent to the emergency room after being mauled by a cat. It was pretty bad. Anyway, he said he was building the Garden of Eden in his apartment. I'm not making this up. Even though you think I am, I'm really not. Everyone can do a Google search now and find it. So let's look at these patterns again. So I want to find patterns of interest, right? And I can say things that I'm likely to find in a house and things that might not be in a house, right? So in that case, I might divide it something like this. I'm sorry. This is, I guess, a division of stuffed animals and non-stuffed animals, right? And I might have been interested in finding things in a house or not in a house, but this is what the computer found, right? So why did the computer find this? Well, I just showed the computer all these images. I said, what patterns do you see? And someone over here said stuffed animals, right? So the computer agreed with you, right? So the computer said, there's no real computer here, don't worry. The computer agreed with you and said, yeah, this is the way I divide up the images, right? So this style of interaction of giving the computer images and saying, what do you see? And it gives us back these groupings. This is called unsupervised learning, all right? Some of you might have heard this term before. And the idea of unsupervised learning is just to look for patterns that are in the data. And we have no examples of what output looks like. I didn't show any examples of a right way to divide these images. I just said, here images, divide them up. The wonderful thing about this is we didn't have to give any labels or examples of what we were looking for. We just had to give the computer images, which is pretty easy to do, right? I can probably download 1 million images from Google, give it to the computer, and the computer can divide them up for me, which would be great. It would be very expensive or time-consuming if I had to actually label pictures and saying, belongs, stuffed animal, not stuffed animal, something like that. The problem here is, though, we can't demonstrate to the computer what we're really looking for. We can't demonstrate output, right? This is where it comes unsupervised. We don't supervise what the computer is learning. So a big application of this would be something like data mining. So how many people have heard data mining? Okay, great. So like Walmart is like a good example of data mining. They have this tremendous amount of data of people buying things, and they want to learn interesting patterns. So they don't say to the computer, here's a pattern, does anything match it? They say, well, what are interesting things that you could find? And the computer says, oh, I've noticed there's spikes here in the data where people in this city are buying this sort of product, right? However, another thing I could do is I could say, well, what I'm really interested in is 2 groups, right? A group on the right, which are things in the house, and a group on the left, which are things that are not in the house, right? I don't expect to have a giraffe, or I guess there's raccoons in my house. Raccoons, I don't want in the house, let's say, but they could be in there. And why would I want to do this? Because I want to give new pictures to the computer, and I want the computer to be able to identify where they belong. So I wanted to show a picture of a gorilla to the computer, and the gorilla would say, well, it belongs in that group, right? So this is a different sort of pattern than the computer found by itself, right? And when I asked people what sort of patterns do you find, this was not something that people mentioned, but it might be something of interest to me. So in order to get the computer to learn these sorts of patterns, I use supervised learning, right? The idea of supervised learning is I will show you output, you being the computer, and you will learn how to generate that output for me, right? So the really nice thing about this is we can learn very complex patterns. So I can come up with these really, maybe I want animals that have eyes looking forward versus eyes face to the side, right? These really arbitrary things. And I could potentially show the computer examples of that, and the computer would learn what to do. And it can do very well. So performance in these models tends to be very good. The problem here is I have to label data, right? I have to show the computer examples of animals that belong in the house, animals that don't belong in the house. And that might be expensive and time-consuming for me to do. So applications of this are things like classification, sorting data into predefined groups, right? And we're going to see a lot of details of this. So most of the tutorial today will focus on supervised learning. So I want to now give a definition of what does it mean to learn, kind of using a supervised definition. So there's a couple things we have to be aware of when we're asking what does it mean to learn. So first is we have input. This is where the math comes in. Okay, I'm sorry. So input is, in machine learning, tends to be x. This means some kind of input. And x is a vector. So for those of you who don't remember, I don't know, math, a vector is like a matrix, only there's one row. And it has a series of numbers in it. So these are real value numbers. That's what this fancy thing means. So x is an m-dimensional vector of real value numbers. And we have n such examples, right? Some number. We also can be given y labels. So label y will be one for each example x. And the y can be a real number, or it can be some predefined set of labels. So a label might be 64, 32, 1.67, right, if we want to output real numbers. Or a label might be something like this animal belongs in the house, or this animal doesn't belong in the house, right? So that's what our input typically looks like, and I'm going to use this notation all throughout. We then have a loss function, right? So h, which I'll define in a second, h of x is what we're going to learn. H is a hypothesis. And what our loss function says is we know what y is, all right, and we have this predictor that given x will output some y. And we want to know how good that was for what we really should have done, right? So if I'm trying to predict belongs in the house or doesn't belong in the house, y might be belongs in the house. If we say belongs in the house, our loss is probably going to be 0, right? We've done nothing wrong. Alternatively, if I'm doing regression, y might be 1, and I might have predicted 5. And we want to have some number that represents how bad that was of us to do, to say 5 when we should have said 1, right? So we want our loss to be 0, and we're going to define it depending on the problem. So we have this. The next idea is this hypothesis class H. So this is kind of a general, generic framework. A hypothesis class just means some theory you can have about what the right thing to do was. So when I said, how do you divide up these pictures, and everyone gave me a different answer, those are all hypotheses. And they were from some larger class that's in everyone's head about all the possible ways I could divide those pictures, right? There's essentially an infinite number in this case. So we assume for most problems that in H, which is our hypothesis class, we have H star. Star usually indicates perfect here. And it's the case that if I added up the loss for H star on all the labels I have, it's going to be less than epsilon. And epsilon is either 0, because there's some perfect way of doing it, or it's going to be small. So in for example, the case of dividing animals by mammal, right? There's some perfect answer. There's some universal correct answer for whether or not something's a mammal or not. You can get everything right. But for example, does it belong in the house or not? We might have divergent views about whether or not something really belongs in the house or not. And therefore, some people, no matter how good they are always going to make some mistake, right? And so that mistake is going to be small. It's going to be epsilon. OK, using these definitions, a learning algorithm is going to do as follows. We have a learning algorithm A. If we give it all of our data, all of our x's and y's, it's going to generate h hat, which is going to be its best guess what the hypothesis is. And we write that to say that h hat is going to be the h such that this term here is the smallest we can make it. And this is the loss. So a good learning algorithm will look at all the different hypotheses that it knows about and pick the one that's going to give us the smallest loss for the data it can see, right? Basically, we showed a lot of examples, and it tries to come up with a theory that works well on all of the data. So that's what it means to learn. a couple points here. So for loss, we use this to measure system performance. So you can think of loss as accuracy, right? Like how many things you get right or wrong. But the loss you pick is really dependent on what you're trying to do. There's this issue with loss in that we care about generalization error, which is overfitting. So for example, if I just showed you that picture and showed you animals, pictures of this type belong on the left, the pictures of this type belong on the right, the correct answer I had in mind was things that occur belong in a house and things that don't. But there were other possible answers, right? And so you could have come up with an answer that was different and gotten the same results. But if I show you new pictures, you and I will disagree, right? That new pictures point is what we call the generalization error. And if you can do really well on the examples I showed you, but you do really badly on new ones, we say you've overfit to the data. Right? You've looked at that data and come up with a hypothesis that fits that data exactly, but it's not really good for anything else. So what we typically do is we take our input, we take some of it and we say that's training data, and we're going to use that to learn H. Some of it is development data, and we're going to use it to tune some parameters of A. Right? A might have some knobs and switches and levers and stuff, and we need to know how to set those. And then we're going to take some test data and save it for the very end, and that way we can test how well we're going to do when we go into the real world. And so once we've done that, we're going to output a model that is going to represent what we've learned. And that model and what it looks like depends on our learner algorithm. OK, so what types of output can we have? We're going to talk almost exclusively about the first one, but you've already seen more than one thing on this slide. So classification basically is just sorting things into groups. You can have binary 2 groups, many groups, which is multi-class. You can be applying, something might belong in multiple groups, which is multi-label. There's lots of different versions of this. A really common example is spam classification. You want to say an email is spam or ham. Ham is not spam, for those of you unfamiliar with ham, the product. That's what it's actually called, ham. And a loss for that data might be like accuracy. We might want to rank things. So we want to order some kind of results by preference. So if you guys have done web searches, for example, there's some preferential ordering we have over results. And we can get computer to learn that. So there we might want to use something like swap pairs, how many things are out of order. That might be our loss. Regression is outputting a real number. So let's say we want to predict the stock price tomorrow for a stock today, that we have information today. By the way, that's a hard problem. I wouldn't recommend trying to solve it. And there something we typically use there is called the squared loss. And structure prediction, which I believe you guys saw yesterday, we don't want to output a number or anything like that. We want to output some kind of large object, right? So that might be a sequence or a tree or some kind of segmentation. So I give you an image, and I want you to identify all the faces in the image, right? So your output is going to be some parts of the image, circling faces or something like that. So the new digital cameras can do that, by the way. It's very cool. So the running example I want to use today is document classification, because it captures most of what we want to talk about. So the idea behind document classification is pretty straightforward. Let's say you have 2 types of documents. It can either be about sports or finance. Right? If you are unclear what sports or finance is, I have an example for you. So sports, the Chicago Cubs played a great game of baseball. Obviously, I made up these examples. Finance, the markets rallied today, sending the S&P 500 to a new 3-week high to start the financial year. If I were to give anyone in the room these documents, you would, without question, label that sports, this finance. We want to teach a computer to do the same thing. This is document classification. These basically represent topics, right? So it's a classification problem, it's binary, and we're going to be talking about a supervised approach, which means I'm going to show you lots of things that look like this, right? Because some of you might not have seen sports. And you're going to learn what sports are and what finance is, and then I'm going to show you things that don't have these labels, and you're going to label them for me, right? That's what we want the computer to do. So the next question I have to ask is, how do we represent data to the computer, right? We have this real world, we have these documents. How do we represent them to the computer? And I'm only going to spend one slide on this because it's a large topic and it really depends on the problem. Something that's very common for NLP, which you'll see a lot throughout the summer, is this idea of bag of words or bigrams. We just care about what words are in the article. We don't really care about their order or anything like that. Right? So we'll take this sentence, the Chicago Cubs played a great game of baseball, and we'll say it has a feature played, great, it'll have Chicago Cubs, Cubs played. We'll generate all these possibilities. Right? Each one of these possibilities corresponds to a dimension in our input examples x, right? So you want to know how big x is, count how many different words you know about, right, in your data. So, maybe 10,000, 20,000 unique words. Each one of those words will correspond to a different dimension of x. So if I give you a vector, there's going to, let's say, a vector representing this sentence might have 20 elements that have a value of 1, and the rest of the vector will be 0. It's sparse, if you will, right? And that's how we represent these documents in a way the computer can understand. Notice we've lost a lot of the information. If I were to give you such a vector, you could not tell me what the sentence was originally because it's all been jumbled, right? But we don't care about that, right? This is just a very simple way of understanding it. Other prompts are very different things. So you're going to learn about speech recognition. We represent things in very different ways there. Images, DNA, obviously, all these things have different representations. But we're just talking about document classification today. So I want to talk about a couple different supervised learning algorithms. You might have heard of some of these. So as I say them, raise your hand if you've heard of them. Nearest neighbors, all right, decision trees, artificial neural networks, perceptron, support vector machines, and, well, probabilistic models. But Gideon will talk about that, so I don't care if you know that. OK, I noticed the same people basically just kept their hands up almost the whole time. So, all right, interesting. We're also going to talk about two unsupervised learning methods, k-means and Gaussian mixture models. And we'll go through those at the end. So for each one of these, I want to give you the motivation about behind the algorithm, talk a little bit about the algorithm, and some pros and cons. So let's start with nearest neighbors. So the motivation here is really simple. We're going basically from simple motivation to hard motivation through these examples. All right, here's what you say to yourself. This document has the same label as the most similar document I have seen, right? So for example, this document is about baseball. The last time I saw an article about baseball, it was sports. Ergo, this document is about sports, right? We do this in our head all the time, right? We take something that we're seeing now, we want to know what to do with it, so we think the most, what have we seen before that is most similar to this? We're just going to do the same thing, right? We use this all the time, so it makes sense that we want a learning algorithm does something like this. And that's what this is. So the approach here is every example where we see, we're just going to save it. And then when we see a new example that we want to know how to label it, we're going to find the closest thing that we've seen before, for which we know the label, and then we're just going to say it has the same label, right? So I give you a bunch of documents that have labels. All you do is memorize them. I give you a new one. You flip through all the documents that have labels until you find the one that looks most like the new one, and you just say it's the same, right? That's it. That's how simple nearest neighbors is. If you don't understand that, here's a picture, okay? Let's say we have blue dots and red dots. And because I'm trying to use the same color scheme, blue is sports, red is finance. So you ask, why are the dots in all different places on the screen? Well, I told you that we represent everything as vectors, so pretend everything has 2 dimensions now. I really tried to come up with an n-dimensional slide. It didn't work, so here's 2 dimensions. And basically, you see these things are floating around the space in various ways. So if I have an example here, right, I don't know what this example is. But what do you guys think it is? Is it a red square or a blue circle? Red square. Why is it a red square? It looks like a square. OK, I would like to point out it has rounded edges to represent circle. So that is not a good reason. But someone had, right, so all of its neighbors are squares, right? So you have no idea what this represents, but you're like, look, it's in the middle of square, so it's a square. OK, that's great. You're right. What about this one? It appeared up there. Blue. OK, you guys have figured out how this works. What about this one? All right, so everyone raise their hand. What do you think it should be? Raise your hand if you think it should be a red square and blue circle. OK. Someone tell me why it should be a red square.
Average.
Average, right? It's next to the blue circle, though, right? So what's up with that? Good answer. Like, that blue circle is probably wrong. So you guys are right. Although I made up this example, so I could have just done a blue circle and, ha ha ha. So this comes up to the point that sometimes it's actually not very good to just look at the closest neighbor. right? Because this graph looks pretty good, right? You guys can do a really good job of identifying things in this graph. But still, we're going to make a mistake if we look at the closest neighbor. So what we typically do is we look at some number of close neighbors, i.e. k. We're going to have that number k a lot, right? So if we look at the k closest neighbors, we'd say, well, this, let's look at 5. 1, 2, 3, 4, 5. 4 out of the 5 are red squares, so this is going to be a red square, right? Then that's the algorithm k nearest neighbors. So there's a couple things that you have to decide if you actually want to build this. How do you measure distance between 2 points? Really good way is Euclidean distance, although depending on the problem, there are other ways to do it. How do I choose k, right? So if I choose a small k, I'm going to have problems like I just showed you. However, k is small means it's very fast. It's really easy to find the single closest neighbor. If k is large, it might be slower, but it's going to smooth for outliers, right? To answer the question here, how do we know we've learned something? So notice, and I just want to point this out, just making sure you're doing well in the training data is terrible, okay? If I gave you the training data, and then I said, what's the right label for this point, and it was in the training data, what you would do is you would look and you would find that the closest point to this one is the same thing, right? And of course, you know the label, so you're going to get it right. So the training error of k nearest neighbors with k of 1 is 100%. I'm sorry, the training accuracy is 100%, right? Does that mean it's going to get 100% on the test data? Of course not. How good is it going to do on the test data? I actually have absolutely no idea. So you have to be careful when you think about training error and test error. In this case, it's a little bit extreme. There is some work on measuring the generalization error of k nearest neighbors, but I'm not going to talk about it now. Another issue that affects all learning algorithms, but I want to touch on here because it's so obvious in this case, is this idea of bias and variance. And in everything you do in learning a model, you're constantly trading off between bias and variance. So this is what happens. As we increase k, and we look at more and more neighbors, our bias will increase. Because the more and more neighbors we look at, the more likely we are to just pick whatever the most popular label is. So if k is everyone, right, then we give you the same answer for every point. And that's whatever happens to be the most popular label in this data set, right? So our bias towards a specific answer will increase as we increase k. On the other hand, our variance will decrease. So variance is how unpredictable your output is, right? So if I have a k of 1, it might be that if I move my point just a little bit, I'll get a totally different answer. So in this slide I showed you here, right? If I took this and moved it a little this way, I get red. If I moved it a little this way, I get blue, right? These little changes mean that your output can have a huge amount of variance, right? So as I increase k, though, right, then basically I'm going to start taking the average, and moving points a little bit doesn't really matter anymore, right? The key is somewhere between a lot of bias and a lot of variance is the right answer, right? And choosing k is about trading those things off. And that's a lot about what we use development data for. We use development data to figure out, well, what's the best k for this problem? So to quickly summarize k nearest neighbor. So pro would be, it's really easy to implement. So how many people think they can implement this algorithm now? OK, don't worry, you're not going to have to. So I'll ask again, how many people think they can implement it knowing that they don't have to? It's the same amount? Oh, OK. I thought more people were like, wow, if you're not going to ask me to do it, sure. It's also pretty easy to understand the output. So if I asked you, you told me this document was sports, why? What would you say? Yeah. So, but showing me words might not be informative. You could say, well, I think this is sports because here's something else, and this was sports, right? And this is just the closest neighbor. And I can read it and be like, oh, I see why these things are similar, right? And this is sports, so I see why this would be sports.
Yeah, so
Right?
if you have keywords in your mind, then you can
Oh, yes.
similarity
Yeah, yeah.
between
Exactly. So it's pretty easy to understand, right? So if you built this algorithm for someone and they complained it didn't work well, you could show them examples and they could figure out what was going on, right? So that's really good. We also can learn very complex functions. So what I showed you was all the blue was at one side and all the red was at the other. But now imagine that basically we have blue here, blue here, blue here, and then there's a pocket of red over here, right? We can learn that too, right? We don't really care where it is as long as there's kind of these groups, we're going to do a good job. And so we don't need to learn a simple function to divide up the space. We can learn these very complex functions. The downside is we have to store every example we've seen. So if I say I want you to learn a nearest neighbors classifier and 1 million examples, you have to store 1 million examples. And anytime you want to use it, you have to keep 1 million examples in memory. That's pretty slow. How do you choose a similarity metric can be very complicated. And if you take the naive approach, you have to compare every new example to every existing example. And that's just a slow thing to do, especially when there's 1 million, right? So k-nearest neighbors, for example, is used sometimes in image classification on millions of things, right? And so how do you make it efficient and deal with those problems? That's not easy. Useful extensions to this, if you're interested, how do you learn similarity metrics? So there's this work on large margin nearest neighbors, where basically you're trying to learn how things are similar to each other. And then I mentioned efficient ways to kind of find and do comparisons. OK, so let's talk about our next method, decision trees. So does anyone have any questions of nearest neighbors before I go on? All right, that was the easy one. These get kind of harder as I go. So here's my motivation for decision trees, right? I can decide about a document by incrementally looking at different properties of that document, right? Now, we do this all the time. So I'm actually going to use a different example. Let's say you want to go to a restaurant, right? So you have a decision tree in your head, right? Am I hungry, yes or no? If I'm hungry, I'm going to go to the restaurant. If I'm not hungry, I'm done, right? So yes, I'm hungry. Do I want fast food? Yes, I want fast food, so I'm going to go to this restaurant. No, I don't. I'm going to have to find a different one. I walk in. Do I have any money on me? Yes or no, right? And then we ask, how long is the line? Is it long or short? Each one of these things is a process that we're going through in our mind that will lead to an eventual decision. And in this case, the decision is eat here, don't eat here, right? And if I asked you to write this down for things like, eating in a restaurant, or should you do your homework for this class, or things like that, everyone can write down these models. So the idea is maybe we can just have a computer learn these models for problems of interest, right? So what we're going to do is have the computer construct a tree of decisions, a decision tree, to follow, where each leaf will be some label, it will be some decision, and each node will be some property of the document that we're going to check. So let's give you an example. So this would be a decision tree for sports and finance. So the first thing we say is, does the document have the word game in it? Yes or no? If it does, we're going to go this way. If it doesn't, we're going to go this way. Right? So yes, it had the word game. So does it have the word baseball? If it does, then we're confident enough it's sports. Right? It had the word baseball and game, it's a sports article. No, it doesn't have baseball. So does it have football? Yes, sports, no, we're just going to say finance. Right? If we've gone this way, does it have the word markets in it? Yes, finance, no, sports. Right? This probably doesn't work so well, but you can basically see how this model works. Right? This is the decision tree. So obviously running it is very, very easy. All I have to do is take a document, check its properties, go through the tree until I get to an answer. Right? How do you build it? Right? That's the interesting part. So probably the most popular algorithm for building decision trees is ID3, and there's some extensions of ID3 that are a little bit better. And basically what it does is it greedily selects the most discriminating feature. Right? So this is basically how their algorithm works. This is a really short outline. Right? It's recursive. So given some examples, given some attribute or feature I'm looking at, and other features or attributes, if all the documents that I'm currently looking at with this feature have the same label, then just say that label. Right? So if the feature is baseball and all the documents that have baseball are sports, then the answer is sports, and we're done. If not, if some are sports, some are finance, then what we're going to do is we're going to build a node that says baseball, and we're going to branch yes or no, right? I'm sorry. Wait, that was okay. So if all the documents are baseball, then say yes, we're sports. If all the documents that say sports that say baseball are sports, then just say sports. Otherwise, we need to find a new discriminating attribute. Okay? So what we're going to do is we're going to find the attribute that we have remaining that best classifies all the examples, right? One attribute that can divide the data in the best way according to the label. right? We're going to add that as a node, add branches yes and no to the left and right, and then we're going to call this again, right? And we're going to call it with that example A, with that attribute A, and all the attributes except for A. So what this does is it starts at the root, it picks the best feature, it sticks it there, and then it recurses on each subtree. And at each point in time, it picks the best feature for discriminating at that level, right? So this selecting the best every time is this greedy approach. So we still have lots of choices we can make. So how big should this tree be, right? Let's say I get to 40 levels. Should I keep going or should I just stop at some point? And that's really tied into this idea of pruning. So if you just keep going forever, you're probably going to learn things that are not very discriminating, right? And we don't care about that. And if you do care about that, it's going to lead to things like overfitting. So we want to prune this tree in some way. And the C45 algorithm, I don't remember why we name things like this, which is an extension here, deals with those cases. We also have this point, how do you pick the most informative attributes? So I said, attributes that best classify examples. Well, what does that mean? And there's different ways of dealing with that as well. A common choice is information entropy, which Gideon might talk about today, but it's not important. There are different ways of doing this. So these are different choices we get to make. So to summarize here, decision trees are really easy to understand. Particularly if I ask you, why did you make this decision? So I want to know, why did you say this was a sports document? And you can say, because it has this word and doesn't have this word. So I said sports. Right? It's really easy for people to understand these. So one of the major areas where these are popular are people who want to understand the output of their system. So these are called white box, right? You could open it up and look inside, as opposed to black box. They're very good at identifying just a few critical features. So even if you have a relatively large tree, you're only going to be using a couple of the features as opposed to all of them. If you have 10,000 features, it's unlikely to have a tree with 10,000 nodes. You're probably going to have 100 nodes or something like that. So it only ends up picking kind of the best few features. And it's very fast to run. All I have to do is check 4 or 5 features as I go down the tree, and I'm done. The downside is it's very slow to train. These algorithms typically are very slow to run. It tends to overfit if you're not careful. If you build the whole tree out, it's going to overfit to your training data. There are certain things that you cannot represent in decision trees. They basically just check, does this attribute exist or not? And that's all you can check. So combinations of attributes, exclusive OR of attributes, those things can't be captured here. So some data sets this might work poorly on. And of course, if this wasn't obvious already, the best tree is, finding the best tree is an NP-complete problem, right? So that's why we're using greedy algorithms here, because we have no hope of actually finding the best tree. That might matter, that might not matter, depending on your data. So a couple really useful extensions of this. How do you deal with real value data? So I'm always saying, does it have or not have this feature? But you can also deal with real value data. How do you, so another extension are decision stumps for boosting. So does anyone here know what boosting is? Anyone heard of it? OK, 2 people. Now we're talking. I didn't even bother including boosting in this tutorial. So boosting is a very interesting algorithm that's motivated by computational learning theory and statistics. It uses decision trees in most implementations. Very simple decision trees called decision stumps. And there's also this work on random forests, which, if you're interested, is kind of an ensemble method where you have lots of trees, i.e. you have a forest. You see trees, forest. All right, we'll come up with a different name. It'll make you laugh. All right, any questions on decision trees before I go on? All right, how many people feel they can build the decision tree today? I gave you the rest of the day off. 2 people? That's it? Really? 3, 4? OK. I'm going to lose the rest of you now. No one's going to be able to build the rest of these algorithms today. But I decided to do the easy ones first. They're easy to understand. They're just not easy to implement now. So artificial neural networks. All right. Now it's time for fun. So here's the idea. Notice the motivation here is now much more general. Right? So the real motivation is like, let's build a brain. OK? But that's not real motivation. Don't worry. So the idea here is we can take linear combinations of the input. So we're going to take different parts of the input, and we're going to combine them together through addition plus some weights, right? Linear combinations. If we then take linear combinations of those, we get this nonlinear output, right? So the idea is we can learn these nonlinear functions through simple linear combinations. We also can do multiple things in parallel. So instead of learning just one thing at a time, there might be multiple things we're interested in outputting. We can do all of those at once. The way we do that is through this motivation of neural networks and how they work in the brain, right? So I'm pretty sure that someone invented this and they realized it was similar to the brain as opposed to someone wanted to build the brain, okay? So nevertheless, there is a lot of hype about neural networks. I constantly meet people who know nothing about machine learning, but walk in and say, neural networks are the greatest thing and they're going to solve my problem. The name here is really chosen well to indicate that these are really cool, powerful things. However, I'm going to demystify them. They are just statistics. They are not actually little brains, and they cannot solve the world's problems. Nevertheless, we're going to keep using the word neural. So our approach is going to be to construct a graph of neural connections. I'll show you what that looks like. It's going to be a network. Some of the nodes will be input and output nodes, and some of the nodes will be hidden nodes. So this is what a neural network looks like. So here are my input nodes. So I said I have this vector x. So here x is p-dimensional. So each value in x corresponds to a node here. I'm interested in learning some output. So I could have lots of output, k output nodes y. So in the examples we've been talking about, we just want to know if a document is about sports or finance. But we might want to know other things. We might want to know, is this a document we got from the New York Times or CNN? And we might want to know, was it written by someone who's a native English speaker or not, right? All those things about the document we could, in theory, learn at once, right? So we have lots of nodes up there. And then in between, we have some hidden layers, right? So this is a single hidden layer feed-forward neural network, which means that it's got one layer, and all these connections have arrows pointing that way, right? This implies that there are more complex neural networks that have more than one hidden layer and feeds going in different directions. But I didn't want to try and draw those on a PowerPoint slide. That would have been ridiculous. So a couple things to say. So basically, we get our input here, and that input propagates to these nodes. So you see each one of these nodes is connected to every node in the hidden layer. Each one of these lines represents some weight, right? So you have m times p, really p plus 1 weights. The plus 1 comes from a bias term, but it's really, you can think of it n times p weights, right? So we have m nodes here, p, so we have m times p lines. Each one of those lines is some weight. What that means is x1 is the number 1. We want to know what z1 should be. Well, it's going to be some weight times x1 plus some weight times x2 plus some weight times x3 all the way down to some weight times xp, right? Some weight. The same is true at the next level. So each one of these now is going to have some value in it that's going to be reflective of that sum. And the y's will do the same thing. So y1 is going to be some number times z1 plus some number times z2, et cetera, right? So if you define the model in this way, learning a neural network is about finding what these sum numbers are or sum weights are, right? So to tell you where the whole neural concept comes from, the way, usually instead of just taking these linear combinations, right? So I said basically you add up a linear combination of all these, and that's what z1 is. So what we typically do is we pass them through a function first, right? So we add up all those things, and we get some number x, and we pass it in this example through a sigmoid function. So if for those of you who haven't seen a sigmoid function before, there's a sigmoid function, right? You will notice it has the following property. Most of the time it is 0 or 1, and there is some small range where it is something in between, right? In this case, basically, if I'm looking at any number greater than -4 or +4, I'm going to see 0 or 1. And then there's some point where it kind of quickly changes between them. How fast it changes, I can control with a scaling factor. So here's a sigmoid function with a scaling factor of 5. Notice the change is much more rapid. As I ramp up the scaling factor, this looks more and more like a step function, right? Basically, when you get anything negative is 0, anything positive is 1, right? So for those of you who know anything about biology, this is where the connection to neural networks in the brain come from. So the way neurons work, at least this is what I learned in AP Bio a while ago, a neuron has lots of inputs to it from other neurons, right? Those other neurons keep firing. At some point, this neuron has seen enough to fire itself, right? So notice neurons don't fire at some combination of their input, right? They don't fire a little or a little more and then a lot. They're either firing or not firing, right? And that decision of when they start to fire is some combination of all their inputs, right? And that's the same thing you have here. So these numbers here, these z's, will either be on or off, right? And they're going to be on once enough of these inputs are on in some way, right? And that determination of enough is defined by this sigmoid function. So this is why it's called a neural network, okay? If we want to learn a neural network, right, we have to learn all these parameters, these weights, right? So if I told you, I want you guys to implement a neural network, and here's the structure, and here are all the weights, you guys could actually probably do it right now, right? The difficult part is I don't give you the weights. The weights are something you learn from data, right? So the way you learn here, and this is a common theme that you'll see through the rest of our slides, is you first define some function that you want to minimize or maximize, in this case minimize. So there's some loss function, and we want to reduce this loss function as much as possible. So I'm going to give you an example of regression. Regression, you want to output a number. And an example of a regression loss function is the squared loss. So what this says is the correct output y. All right, so I here is the example. In k is the output. So you have lots of outputs, lots of examples. So for the ith example, it's kth output, right? What number should I have output? And this is what I actually output, right? So I have a function for my output k that's going to be summing all of these weights, sigmoid functions, all that. If I pass an input to it, it's going to give me some number. So tell me what the difference between those two numbers was squared, and add up all of those, right? So if this whole thing is 0, it means we were dead on accurate for every output for every example, right? So what we want to do is we want to minimize this term. The smaller we make it by setting weights, the better it's going to be. So our goal is now to set weights such that this becomes 0. So the algorithm to do this is called, well, one of them, but probably the most common one is called backpropagation. So does anyone remember, you guys learned about HMMs yesterday, right? Okay, does anyone remember how you train an HMM? What's the name of the algorithm? EM, forward, backward, both are right. Forward, backward is an EM algorithm. So both are on the slide. So backpropagation is actually very, very similar to it. So what you do is you do gradient descent on R. So does anyone know what gradient descent is? Yes? Yeah.
So it is y minus d. We calculate d equal to wi sigma wi xi. Then we differentiate it. Put the put the dy by dx equal to 0, and then finally find out the delta to find out the delta I for kth layer in the back propagation, and find out finally the weights using the formula.
Okay, that's a much better answer than I was expecting from anyone. Do you want to switch? That's very good. So let me give a much simpler answer. So the idea behind gradient descent is you have a function. Right? Imagine a convex function that looks like, that was very good, by the way. I'm very impressed. Are you an undergrad or a graduate student? Undergrad? I'd be afraid if I was a graduate student. No. So imagine you have a function that looks like this, right? It's convex in that, well, without giving the definition of convexity, it's like an umbrella turned either right side up or upside down. We call them both convex. Okay? And basically, if I take the derivative of this function at this point, it's going to be a number that's pointing me in a direction. And it's going to tell me what the slope here is. Right? And as long as I figure out what the slope is and climb, I can keep following it until I reach this point. Right? So here is a maximization, but you can imagine I can invert it and we have minimization. So that's gradient descent. So we do gradient descent on this loss function. So this is not a convex function. Right? This function looks much more like this. So it depends where we start. Right? If we had started over here, we would have gone to there, and this might be better, but that's not important at the moment. And the idea of backpropagation is that we're going to sweep forward and backward over the network. Forward-backward algorithm, HMM, you see the connection? Where at each point, we only need to compute local values, again, similar to an HMM. And we basically fix the output, we estimate the weights, we fix the weights, we estimate the output, and we go back and forth like this. And we can, using gradient descent, come up with an answer. The problem, as I said, You have local minima, you can overfit the data, and where you start here makes a huge difference, but no matter. That's the idea behind backpropagation. So if you've seen an HMM, you kind of have an idea of how it works, although I'm not going to go into all the details for how to implement this. The choices you need to make in implementing a neural network are what learning algorithm you want to use. So I gave you the example of backpropagation, but there are others. How long it takes to train being one of the things you might care about. What structure should your network have? So I just said you had a single feed-forward neural network, single hidden layer feed-forward neural network. There are many, many other things you could have done, and those other things tend to work much better depending on the problem. How do you choose the right one is non-trivial. How many nodes are in the middle also? I just said there are, m nodes, but who knows how many nodes we should have. What loss function we want to minimize. So squared loss is pretty good for regression. Classification uses something called cross-entropy, which Gideon might touch on today. But there are others we could use. Also, there's different network types. So I said we use the sigmoid function, but we don't have to use the sigmoid function. There are other functions, such as radial basis functions that we could use, and many, many other things. So the amount of decisions here are actually quite staggering to actually implement one of these things. So quick summary, neural networks are great because basically they can do nonlinear functions, and they can output multiple things at once, which is both really great things. But they're very hard to interpret what happens. So let's return to my example. I give you a sports document, and your network told me it was finance. And I said, why? How would you answer that question? Yeah. It's great. You can output the weights, right? And basically say, here are the weights, and here's the functions to combine them. But no one actually understands what that means, right? So you basically shrug your shoulders and be like, look, I don't know. I don't know why I did that. And for sometimes that's great. Sometimes that's really a problem. Extensions, so I'm not exaggerating. There are entire conferences and journals dedicated to neural networks alone, right? So there are many, many things you can do. Just answering these questions, you can imagine there's a lot of different potential answers. You can apply this to supervised and unsupervised learning. So this really has a number of applications. And something to specifically mention, there's been recent work on what's called deep belief networks. And if you are interested in neural networks, this is a really good place to start. Work by Jeff Hinton and some of his students and collaborators trying to resurrect the popularity of neural networks and show that they really can be much more powerful than what we've previously used them for. OK, any questions about neural networks? Yeah, I've actually got a lot of questions about them. But do you have any questions about neural networks? OK. So I want to go back to this neural network and use it as an introduction here. So we can actually make some simplifications, right? So the first thing we can do is we could say we only have one output, right? The problem we were talking about, document classification, we don't have lots of output. We have one output, so fine. We still have a single hidden layer feed-forward neural network. We just have one output. And let's say that I defined my weights to be, I defined it such that for every x, I have one z, right? That's a neural network. And for every x in z, the weight will be 1 if x1 and z1, if that's the match. And it will be 0 for everything else. So effectively, I only have these lines. Right? I'm sorry, I don't have z3, but it's there. Okay? So I still have a neural network. All I've done is removed an output, and I've set a bunch of my weights to 0. Right? So let's observe that if I've done that, there's really no point in having these z1 layers. Right? I'm still learning these numbers here. I still get to learn those. But these numbers here I don't learn. So z's and x's are equivalently the same now. Right? It's just the same thing. So I can get rid of the z's, and I can hook up the x's directly to y. OK. Does anyone know what this is? You do. But what? Someone say? Right? No, it could be from the picture, but it's not. Yeah.
Yeah, the thing is that if we take out only one step, then it would be same as the linear discriminant function. If we won't apply R into a sigmoid function, it would be ANN would be same as the linear discrimination if we won't apply the sigmoid function. Right.
So it could be interpreted as that. What I'm thinking of, right, none of these are wrong answers based on the picture. The picture is ambiguous. I'm thinking of is the perceptron. Okay. The key here, the hidden, the trick of being able to predict that this was the perceptron, is, does anyone know another name for neural networks? They're called multi-layered perceptrons. Okay? The reason they're called multi-layered perceptrons is this is a perceptron. If you don't know what that is, I'm about to explain. All I've done to create the hidden network is I basically layered perceptrons on top of each other. Right? And actually, this work started as perceptrons, and it was only later that people extended them to neural networks. So the perceptron algorithm was actually invented in 1958 by Frank Rosenblatt at Cornell. And he was working on learning in the brain. And his goal was basically to build a machine that was able to learn like the brain could learn. And he literally built a perceptron. So there was a large machine built with IBM that was called the perceptron. And for every dimension of your input, there were these large drums that, I don't understand how these things work, but they turned in certain ways that represented some number for the input. Right? And what the machine did was it learned how to combine all of these things together and produce some output. And the perceptron could actually learn some pretty basic functions. Right? And the idea was this was the foundation for how the brain worked in learning. So a little bit of background, there was a book written about perceptrons that proved that they were very limited. They can only learn linear functions. And therefore, they could never hope to be useful and learn kind of how the brain does. So everyone stopped using them for a while. And then people discovered that if you just stacked them in interesting ways, you could actually learn really, really complex things. Right? And then everyone started using them again. However, the perceptron, the reason I'm talking about it, is while it's the oldest algorithm, it's still one of the most effective algorithms. So in the past, 60 years, 40 years, 50 years, we've improved, but we haven't improved that much over this algorithm. That's how good it is. And many of the problems that you can work on, while perceptron might not give you the best answer, it will give you a very good answer. And it's useful to know because it's a really, really simple algorithm. Right? So I'm going to do this whole algorithm on basically one slide. That's how easy this is. Right? So we're now going to have linear classification, right? No nonlinear output. Our output y is going to be the result of taking w, which is now a weight vector. So if you notice, I reduced the neural network down to one layer, which means I just have one vector of weights. Right? And that vector is going to be the same size as x. So what I do is I take the linear combination of w and x, which is the dot product. That will give me a number. If I want to know binary classification, positive or negative, I just check, is this number positive or is it negative? And that's my output. Right? So if I were to give you w, for any x, you can give me output easily. Take the dot product. If this is in MATLAB, this is one line. If it's Java, you have to write a dot product function. But we can all do that. So the question is, how do you learn w? Right? And what makes the perceptron unique about all the algorithms I'm talking about today is you incrementally learn w. For every instance, for every example, you just look at this one example and update w accordingly. And then you throw that example away and you move on to the next one. And the goal here is to minimize the number of mistakes that the algorithm makes. So binary classification, you can either say sports or finance. We want to minimize the number of mistakes it makes in that. Right? So it turns out if you do this, minimizing the mistakes, you can get a stochastic gradient descent algorithm. And what stochastic gradient descent is instead of looking at all the data and taking the gradient, you look at a single example and take the gradient. And if you do that, you get this formula here. And this is the entire formula for learning a perceptron. What this says is, when I make a mistake, that's the key here. First, I do this prediction, and I say, did I make a mistake or not? If I've made a mistake, then I need to do something. I need to fix it. It's called mistake-driven. If I got it right, I'm fine. So what do I do when I make a mistake? I take my old weight vector w at time I minus 1. I take my example x, which is going to be a vector of the same length as w. Right? Y is going to be positive or negative 1. Right? That's it. So what this means is I'm either adding or subtracting x, depending on what it should be. And I add or subtract x to w. And that's my new w. That's it. Right? What this is, again, I have w, I want to update it. I got this positive example wrong. I take x, add it to w. If I got this negative example wrong, I take x and subtract it from w. That is the entire algorithm. All right? So it is obviously very, very fast and very easy to implement. I'm not joking. At Penn, we gave this to freshmen in Java to do as a homework assignment. Right? So I'm not going to ask who can implement it, but everyone in this room can implement it. Okay? So I want to show you the geometric motivation for this. So let's go back to our circles and squares. So now this line down the middle is a separating line, right? It separates the space, right? And what I'm trying to do is learn this line. So typically, though, I said we have n-dimensional vectors. So instead of having 2 dimensions, this space is really some very large number of dimensions. So really, this line is not a line. It's a hyperplane, which is a plane, but it's super, right? Which means it's in larger than 3 dimensions, right? So we call this the hyperplane. So we have an existing hyperplane that's discriminating between our data, and everything's correct. And we get a single new example. Right? And this example, let's say, is wrong, because part of it really, let's say it's on the wrong side of the line. Right? So what the perceptron algorithm does is it updates this to find a new separator based on that example. Now, in this case, this was good because now everything is right. But there's nothing to say that all these other points will still be right. The key is this point here has to be right. Right? Now, that might be bad because doing that update might get other things wrong. But in practice, this really works very, very well. Right? So that's the motivation for geometrically for how the perceptron works. So even though it's very simple, it has this really nice guarantee which says that if there's such a hyperplane that separates this data, if it exists, the perceptron algorithm is guaranteed to find it in some finite number of steps. Okay? So if you can separate the data, perceptron will separate that data for you. Right? Now, there's a couple problems. One, finite can be a very large number. 1 billion is still finite. So sometimes it takes a while to converge. Another problem is there could be many correct hyperplanes, and I don't know which one it will find. It will just find one of them. Maybe some are better than others. And sometimes the separator doesn't exist. In that case, the perceptron algorithm will never converge, and it will just bounce back and forth. Right? And so things like outliers, i.e. noisy labels, are going to be a problem. So that's the perceptron, and it's a good bridge into the next step, which is supported vector machines, which solve basically a couple of these problems. Which is the correct hyperplane, converging fast, and converging on non-separable data. So before I go on, does anyone have any questions about perceptron? No? OK. So again, this is similar to perceptron, only support vector machines, or SVMs. Oh, yeah, go ahead.
I just had a quick question. So you said that perceptron works really well in practice.
Yes.
I mean, it gets you very close to optimum.
Yeah.
Is that still true of non-separable data? Like, would you still use it as a
No, a non-separable data. So in practice, so it's not non-separable data. There's no guarantees of what you're going to get. So if you look at some synthetic experiments, you can get really disastrous results. However, if you look at a lot of like NLP data sets that are oftentimes non-separable, the perceptron still does very well. So there are reasons for this. So I kind of fudged this point, but I said that after you make this update, you now get this example correct. But that's not necessarily true. So I said that all you do is add x to w. That might not be enough. All it does is move you in the correct direction, but it's not necessarily that's to give you the right answer now. So what that means is that outliers will push you in the wrong direction, but they can never totally spin you out of control. Right? So if you have like a million examples and only one is wrong, then it doesn't really matter. Right? So as you run the algorithm multiple times, whenever you get that one example, you're going to have to update because you're going to be getting it wrong. But after a million things, you've kind of smoothed out. So in practice, it does very well. There's also things like you can control the rate at which it learns. So I just said you add x to w. But you can also say how many times you add x to w. And that can make you learn slower or faster. And there's a lot of extensions on what's called the voted perceptron or average perceptron, which say that the final perceptron you learn should be an average of all the perceptrons that you had all along the way. And what this does is it says, well, the one you ended up with might not be the best, but if we kind of take the average of all the ones that you had at any point in time, that's going to be better. And that usually also really helps performance. So if you look at some papers, like an example would be Mike Collins' paper on structured learning with perceptrons, which is now used ubiquitously in the NLP community. He gets results that are very close to kind of state of the art. And what makes it attractive, it's a very simple algorithm and it's very, very fast. So it's oftentimes something that you can do very easily. Any other questions? OK. So support vector machines. So what we're trying to do now is try to answer this question of what is the best way to separate the data. and we have this maximum margin principle. And I'll show you an example of what that means. But the idea is the best separator separates the data not only correctly, but with the most space between it and all the examples. Right? It creates space between them. And I'll show you why that's good. And the way we're going to do this is we're going to define an optimization problem, and then we're going to learn using the optimization problem what's the right way to separate the data. So let's go back to our picture. So this was the line that we had separating the perceptron, that this perceptron learned. However, these lines are also perfectly good. Right? Let's call these lines 1, 2, and 3. Which one would you pick? 2, 2. Anyone want to say 1 or 3? Yeah, not want to ask it like that. OK. So the perceptron happened to pick 3, which is perfectly good. But looking at all the data, it turns out that 2 is probably much better. Why is 2 better? Yeah.
Can accommodate future examples most easily?
Yes. So here's, oops, wow, one more animation to go. So this is the margin, the distance between a point and the line. So the margin here would be the distance between this point and this line. And I would postulate that this number 2 has the maximal margin of all these things, right? The total distance between the middle line and all of the points is the greatest. And you said because it can handle future examples like these, right? So are these examples consistent with what everyone thought where examples could be? Like these examples aren't surprising to anyone in the room, right? However, they're very surprising to 2 out of these 3 lines. And this happens all the time, right? We learn some separator, all the examples that we can see are right, but the examples we can't see are wrong, right? Because they're just closer to the line for whatever reason, right? So in that case, really the right thing to do is to pick this middle line, because this is the maximum separator on the training data. That is the idea behind support vectors. Yes?
Does that matter? Because you're going to generate a new line and you get new data.
Well, so the idea here is that the new data we don't get labels for, right? So we get all the data points that are fully shaded in, right? And then I have to learn something on that and give you the result. Now you're going to start giving me points that I don't get to see the labels for, that you actually want to classify, right? You're going to start downloading documents from the web, and you actually want to classify them. Those documents might be these points here, these kind of faded points, right? So you don't know what those look like, because you don't get to see them, right? But your guess is that they could be, looking here, it's likely that there's a blue circle here and a red square here versus, red squares go all the way out, much closer to the blue circles, right? You kind of split the difference. Right? And that's the idea behind the max separator. Right? You kind of split the difference. OK. So support vectors. So why is it called support vectors? It turns out, I'm not going to go through the math, but you can write this problem finding the correct separator. That correct separator can be expressed as a combination of all of your input examples. Okay? Those input examples, therefore, are called support vectors because they're supporting the separator. Now, if you think about it, this is not surprising. Think about the perceptron. That weight vector you learned is just a combination of all the x's that you saw. Right? If I start with all 0 weights, to get to the point I'm at now, I must have added and subtracted x's in some way. So I can take all of my x's and have some coefficient, let's say alpha, right? An alpha for every example, and add them all up, and I'll get my weight vector in the perceptron. The same thing is true in support vector machine classification. Right? My weight vector is a combination of all of my input vectors. So we call it support vectors. Right? That's where the name comes from. This problem is a quadratic programming problem that's convex. All that means, and all you have to care about, is there are many, many ways to solve it exactly. Right? And so solving support vector machines is a whole lecture unto itself. It's a whole thesis unto itself. But there are many ways to do it. Something that's very nice about what I'm not showing you is we can tolerate outliers. So I said that the correct classifier to select, the correct hyperplane to select, has the maximum margin. Right? So what happens if a point is on the wrong side of the line? Its margin is going to be negative. Okay? I didn't say anything about what the individual margins could be. You could have a couple points that have really, that had negative margins. But as long as, on the whole, this separator maximizes the margin of everything, that's fine. right? So it might be that one separator gets a margin of positive on all of the points, but overall that's a small number. Another one might get a much larger total number, but a couple of points in there is negative, right? You can imagine such a thing happening, right? So let's say, going back to the slide, I had a single red point, or a red square over here, right? So I could imagine some crazy line I can draw that goes around and gets that point right. But it's probably that one is wrong. So all it's going to do is going to be a negative margin, right? And as long as I'm maximizing everything overall, I'm fine, right? So this formulation can allow outliers. So we've solved the outlier problem in perceptron. This is much more efficient as far as we, in theory, need less examples in the perceptron. What were the other problems with perceptron? Speed, outliers, and which one to select, right? So that's SVM learning. In summary, these do very, very well in practice. They're very good. They're state-of-the-art in many, many data sets. It's a pretty efficient way to do learning. We have the same hard-to-interpret results. We kind of just get weights on vectors, and we don't really know what those mean. Scaling to large data sets is a problem because of the way this is typically implemented. Without going into details, there are ways around this, but it's a challenge. There are many extensions. So some people might have heard of transductive support vector machines or semi-supervised, S3 VMs they're called. So that's how you incorporate unlabeled data into this. We can use them for regression, one-class classification, which is kind of outlier detection. And also, I'm not going to touch on this at all except for to say you can use kernels. And kernels, again, whole journals, whole conferences, whole chapters of books on what kernels are. Kernels allow you to learn nonlinear separators for SVMs. I don't want to say anything else about kernels. If you're really interested, literally, there's whole books on kernel methods. You can get them. So far, I've only talked about supervised methods. And I want to spend the remaining 10 minutes I have talking about unsupervised methods. So the reason is because there are many, many applications that we don't have labels for, right? Why don't we have labels? Labels cost time and money to create. And sometimes you don't have time or money, or interest, or desire, or what have you. We have some very, very large data sets. So for example, to give you an NLP example, people typically use the Penn Tree Bank for a number of tasks. The Penn Tree Bank has 40,000 sentences that are carefully annotated. That sounds like a lot, but if you ask me to get a lot of data, I could download from Google millions of sentences in a couple hours. So 40,000 is a relatively small number of sentences. Those 40,000 sentences took 5 years to build. Does anyone know? And several $1 million. Okay? So clearly, the unsupervised methods could save us a lot of money and time. And what they're going to do, like the example I showed in the beginning, is they're going to discover kind of natural patterns in the data. So the equivalent example for document classification is document clustering. Right? I have some documents, and I want to sort them into groups where I don't have any examples of what those groups are. I just want to find natural groups. Our hope is that natural groups will correspond to topics, and it actually turns out to be the case for newspaper articles. Where if I just say sort this into 2 groups, and they really are sports and finance articles, the algorithm tends to put sports in one place and finance in another place. So the well-known clustering algorithm people use is called k-means. So how many people have heard of k-means before? OK, so that's what I mean by well-known. For example, how many people have heard spectral clustering? Aha, now you see k-means is well-known. No one's heard of the last one. Great. So the idea here is we're going to keep our points in high-dimensional space, just like we've done the whole time. Our x's are high-dimensional vectors. But now I want you to picture them floating around in some high-dimensional space in your mind. And we hope that things that belong together in the same group end up close to each other in that space. So what we're going to do is we're going to find k clusters that best describe this data. K you get to choose, so let's say it's 2. Each cluster is going to be defined by a centroid, which is just a mean of that cluster. And examples are going to belong to the cluster that has the closest mean, the closest centroid. So let's show a pictorial example. Here's my data set. I need to find 2 means in this data that best explain the data, right? So good means would be something like that, right? somewhere around here there's a mean, and somewhere around here there's a mean. If I draw a circle around those points, I'm going to get something like this. And that does a pretty good job of representing my clusters. Most of the blue points are kind of around there. Most of the red points are kind of around there. Right? The goal of k-means classification is to find what those 2 points are, what those 2 stars, hyperstars, whatever. That's it. That's like the whole algorithm, how to find those 2 points. Right? And we want to find them in such a way that all of the points we can see are close to one of those 2. Right? So putting a mean here would be pretty bad. Right? So the means kind of go in the center of where the clusters are. So how do we learn that? So given k, I'm going to tell you how many k there are, 2. Find the best k clusters that represent the data. Let's assume Euclidean distance. This is it if you guys don't remember what it looks like for measuring distance between points. Right? We don't have to, but Euclidean is fine. If I do assume Euclidean distance, I want to minimize what's called the cluster scatter. Right? So what is the cluster scatter? Let's look at it. So C star, again, that means the best clustering. So find the best clustering such that for all the points I that are in cluster K, so all the points that I think are in cluster K, how far are those points from the mean of that cluster, m sub k, right? So that's going to be a number. Weight that by how many points are actually in that cluster, so the bigger clusters matter more, and sum over all the clusters. So if this is 0, that means every single point lies on its mean, which would be great. It doesn't happen, right? But the smaller this is, the closer every point is to the mean, right? Which is good. So all we need to do is minimize this. So how do we minimize that? We're going to use an EM-like algorithm. I say EM-like, it's not because it doesn't have probabilities, but OK. Obviously, if this wasn't obvious, there are multiple best answers here, and this is highly non-convex. But EM is going to help us find a point. So if you guys remember EM, you can follow along with me. In the expectation step, what we're going to do is we're going to assign instances to the closest clusters. In the maximization step, we're going to compute the means of those clusters based on what we've assigned to it. And then we're going to repeat. Right? Recall, EM minimizes the objective. Right? So this will this will reduce the cluster scatter. EM will absolutely converge to an optimal value. However, that optimal value is not necessarily globally optimal. So we can run EM, we can run k-means many times. Each time we might get a different answer. And what's helpful is to run it multiple times, get a different answer each time, and take the best answer. Right? And what gives us a different answer depends on where we start, how we initialize the data. So again, I said bias and variance show up everywhere. I want to show you how they show up here. Right? So k, again, is going to be my model parameter. It's going to tell me how many clusters I have. Right? So the more k I have, the more complex of a model I have. Right? So this impacts bias and variance. So if I have smaller k, then what's going to happen is everything's going to be biased towards the popular clusters. If I only have one cluster, right, then everything's just going to be biased towards that cluster. Right? It's easy. The larger k I have, the smaller bias. Everything has a better shot of being its own cluster. Such that if k equals the size of my data set, everything gets its own cluster. Variance is going to behave in the opposite way. So the larger k I have means the fewer clusters means I only can give you fewer and fewer outputs. So if a k of 2, I can only give you 2 possible answers. If a k of 10, I can give you 10 possible answers. So my variance is going to be much smaller if I have a smaller k. Right? And the opposite as well. If I have a k of equal to the number of clusters you have, then any new point is going to be its own answer, which is a very high variance. Right? So ideally, we would know the exact number of clusters we have, and we'd set k to be that. That's never how it works, though. So again, we need to use development data to pick k. So the last thing I want to talk about is a version of k-means. You can think of it called Gaussian mixture models. And the reason I want to talk about this is you guys will be implementing this afternoon in lab. Okay? So the idea here is very, very simple. Oh, I'm not on that yet. No, I am. So the idea here is very, very simple. I said that each group should be represented by some cluster with a mean. But the problem is that means every cluster is effectively like the same size geometrically, right? I don't have any sense of how far away from the mean those points can be. I just say they should all be close to some mean. But it might be the case that some clusters are much tighter and denser, and some are much, much looser. Right? A natural way to represent that is with a Gaussian, right? So for those of you who don't remember, a Gaussian looks something like this, right? If you've been graded on a curve since high school, you know what a Gaussian looks like. You know, that's basically what a Gaussian looks like. This is y of 0. If I said that this was the mean of my cluster, most points are going to be close to the mean, and very few points are going to be far away. So if this is a probability distribution, the probability of an example being here is going to be very high. And the probability of an example being all the way out here is very low. Right? So now what I want to do is I want to find k Gaussians, right? And these are high dimensional, so you can rotate this out, and every dimension can have its own variance. Right? So some dimensions might have a lot of tolerance, some might have little tolerance. Now imagine I want to learn k of these Gaussians, where the mean of the Gaussian is going to be the center of the cluster, the same as for k-means. And the variance is going to be, if you think about it, the size of the cluster, the density of the cluster geometrically. The other critical step here is instead of saying this point belongs to this cluster, period, is I now know what the probability of that point is being generated by that cluster. And I also know the probability of that point being generated by another cluster. So it might be this point belongs to this cluster in the sense that this cluster generates it with probability 99%, and this cluster generates it with probability 1%. But when I write out my model, both clusters have an impact in possibly generating that example. So I can learn my clusters using EM. Right? And this is what you guys will be doing this afternoon. So you guys will see the equations today. So in the expectation step, I want to compute the responsibility of every cluster for generating that example. Right? What's the probability that cluster 1 generated this example, cluster 2, cluster 3? And that will give me, among other things, the probability of this example being generated in my model. Right? But it will tell me how I can assign responsibility. Right? So this is a soft clustering. I don't say this point belongs here. I say this point belongs here, with this probability belongs here, with this probability, et cetera. In the maximization step, I fix all of those assignments, right, these soft assignments, and I say, well, given all the things that are assigned to cluster 1 with the responsibilities and weights on that, what is the best mean and variance to account for those examples, right? And that's pretty easy to compute. You'll see these are very easy equations to compute. So in this step, for every example, I compute what the probability is, what the responsibilities are. And in this step, I want to update my means and my variances, right? And Gaussian mixture models are the subject of this afternoon's lab. So any questions on Gaussian mixture models, knowing that you're going to all implement one in a couple hours? You'll see the equations, so don't worry. Type in Gaussian mixture model into Google. I don't know. Wait a couple hours, maybe one of these people will post their code for you. OK. Any other questions on that? All right, so I want to wrap up. So I just want to say that there are other ways we can do supervision. So I've talked mostly about supervised learning. I said a little bit about unsupervised learning. But there are lots of other things in between. Right? So you might say, well, I've got some very large data set, and I want to label it, but I only want to label some of it. What can I do? So we call that semi-supervised learning. Right? I have some labeled examples and many unlabeled examples. And I think Gideon's going to give you some examples of semi-supervised learning. Something else I can do is I have partially supervised learning. So let's say an article can either be sports or finance or weather or international, something like that. And I don't tell you this article is sports. I tell you this article is either sports or weather. I'm not sure, but it's one of those two. So there's some amount of supervision here. Right? How do we do that? We can also have semi-supervised clustering. So I tell you, I don't know what the clusters are, but I do know there are two. And I know each one of those clusters has a couple documents, and here they are. Right? How do we run k-means or Gaussian mixtures with that information? You can imagine some straightforward ways of doing that. And there are many other types. So I just want to give you the idea that there's things in between here. And there's a lot of really interesting work on dealing with things in between. So if you're interested in more machine learning stuff, here are some very good books. The first book is more of a statistical bent. The second one is more of a computer science bent. The third one is an older book. It's about 10, 12 years old. So it doesn't cover a lot of statistical methods, but it gives you a good idea of some kind of oldies but goodies, like k-nearest neighbors and decision trees and things like that. And if you have any questions, you're welcome to contact me at my email address. That's it. Any questions? No. Okay. So I'll be here for another 5 minutes. So I guess we have a break for a couple minutes now. So if anyone wants to come over and ask me questions in the next 5 minutes, you are welcome to do so. And thank you very much and good luck today.